today's problem from central orbit of particle dynamics. Now the problem is a particle moves with a central acceleration mu by distance whole cube is projected from an apse at a distance with a velocity capital V, so that the path is r cos hyperbolic root under mu minus a square v square by a v into theta, this is equal to a, or r cos of root under a square v square minus mu by a v into theta, this is equal to a, according as v is less than or greater than the velocity from infinity. Okay, so here it is given that this is the central force. Okay, so central force P per unit mass, this is equal to mu by r square. R be the distance of the particle from the center of force, and it can be, this is r cube, and it can be written as mu into u cube, since r this is equal to 1 by u in central orbit. Okay, we draw a rough sketch of central orbit. This is the central force P, and this is the central orbit O. Okay, and this is the position of the particle. This is r theta. Right. Now we know that the differential equation of central orbit in polar coordinate is given by, this is h square into u plus d2u by d theta 2. This is equal to p by u square. Okay, originally this equation is given by u plus d2u by d theta 2. This is equal to capital P by h square u square. Now by putting the value of capital P, we get mu into u cube by h square u square. So this is mu into u by h square. Okay, and we multiply both sides by 2 into du d theta and get the result as h square into 2u du d theta plus 2 du d theta into d2u d theta 2. This is equal to mu u to du d theta, and we write this result as h square into d theta of, this is u square and this is du d theta whole square, right? And the right side is 2 mu into u du d theta. Now integrating, we get the result as h square into u square plus du d theta whole square. This is equal to mu into u square plus c. This is an integrating constant. This is integrating constant. Okay. Now it is given that here the initial condition at an apse at a distance a. Okay. So for the apse, r this is equal to a, so u this is equal to 1 by a, and we know that from the property of apse du d theta, this is equal to 0, and v this is equal to capital V. It is given with the velocity capital V, and putting the value of this initial condition which are given in our problem, we get from this relation as, before putting this value, we also put here another value which is the velocity expression in central orbit, and we know that velocity expression in central orbit is this equal to v square equal to h square into u square plus du d theta whole square, right? So we put here, this is v square, this is equal to h square into u square plus du d theta whole square into mu u square plus c. Okay. Now putting the value, we get this is v square, this is h square into 1 by a square plus 0, this is mu by a square plus c. Okay, and from this relation we get this is v square is equal to h square by a square, implied h square equal to a square v square, and also we get c, this is equal to v square minus mu by a square. So v square a square minus mu by a square, we get these two results. Okay, now we putting these two results in place of c and in place of h square, we get from this relation, this is the value of h square, so we put a square into capital V square into u square plus du d theta whole square. This is equal to mu u square plus c, this means v square minus mu by a square, right? And we get u square plus du d theta whole square, this is equal to, we get mu u square by a square v square plus a square v square minus mu by a square into a square v square. Okay, from this relation we get this is du d theta whole square, this is equal to mu into u square by a square v square minus u square. We write u square in the right side plus a square v square minus mu by a to the power 4 into v square. Okay, so from this two factor or this two term we get, this is we take common u square and get mu minus a square v square by a square v square plus, this is also, if we write here minus mu minus a square v square by a to the power 4 v square, and getting the result as mu minus a square v square by a square v square, and we get u square minus 1 by a square. Okay, so we get the result is, we write here, this is equal to mu minus a square v square by a to the power 4 into v square into u square a square u square minus 1. Okay, we get du d theta whole square, this is equal to this. Okay, now we calculate this term. What this term is, velocity from infinity. What is velocity from infinity? If a particle start from rest from infinity distance, okay, let it be infinite distance and the particle will start from rest from the infinite distance and moves in a straight line to the point P. Okay, and here the force or law of force is also the same as the given, and here law of force is mu by distance q, that is we take x cube. Okay, and we know that this velocity is given by v dv dx, and this is equal to minus mu by x cube. If we let v0 be the velocity from infinity at the x, okay, that is at r equal to a, Then to find the velocity from infinity v0, we have to integrate this relation from x, this is equal to infinity, to a, this is mu by x cube dx, and in the left side this is v dv, and the velocity is v, this is equal to 0, because we already say here r equal to infinity and v, this is equal to 0, and at an apse we say the velocity from infinity is v0, so this is v0 here. Square by 2, and the range are 0 to v0, and the right side is mu by 2x square, the range is infinity to a, right? So this is v0 square by 2, and this is mu by 2a square. So we get v0 square, this is equal to mu by a square. Okay, this relation gives the velocity from infinity. Now our given condition, this is our given condition, we get v less than or greater than v0 here. Okay, now putting the value of v0, that is we first here done v square less than or greater than v0 square, so we get v0 square means this is mu by a square. Okay, that is we get a square v square, this is less than or this is a square v square, this is less than or greater than mu. Okay, and from here if we apply this condition, first time less than or second time greater than, we see that we get two cases. Now we write the given result here. This is the given result, du d theta whole square, this is equal to mu minus a square v square by a to the power 4 v square into a square u square minus 1. This is the main relation, and we have to integrate this relation to find the curve, and from here we get two cases. Case 1, this is a square v square less than mu, and in case 2, a square v square greater than mu. Okay, now in case 1, it is clear that a square v square is less than mu, so this term is positive. So we get du d theta, this is equal to plus minus root under mu minus a square v square by, this is a square v square, this is a square v, because this is a to the power 4 v square, so outside of the root this is a square v, and root under a square u square minus 1. Okay, now taking negative sign, okay, we get du by, this is minus root under a square u square minus 1, and we write in the right side root mu minus a square v square by ab, and we write here a. Okay, and from this relation, if we taking integration on both sides, this is d theta also. Clearly this is the formula of cos hyperbolic au. Okay, because if we put au, this is equal to z, then a du, this is equal to dz. So for this reason we multiply a from this side to this side. Okay, and the right side is root mu minus a square v square by ab into theta plus a integrating constant, let it be a1. Okay, now initially when theta this is equal to 0, then u this is equal to 1 by u. This formula is not cos hyperbolic only, this is cos hyperbolic inverse, right? And we get the result as cos hyperbolic inverse, this is 1, and the right side is 0 plus a1, and we know that cos hyperbolic inverse 1, this is equal to also, this is 0, so we get So we get a1, this is equal to 0. By putting the integrating constant a1 here, we get the path of the particle as au. This is equal to cos hyperbolic root mu minus square v square by av into theta. Okay, and this is a by r. This is cos hyperbolic root mu minus square v square by av into theta, and we multiply r from the left side to right side, and we get the curve as a. This is equal to r cos hyperbolic root under mu minus square v square by av into theta, and this is our first result. Okay, that is the result for the first case where a square v square less than mu. And similarly for the second case, it is clear that this term is negative when mu is less than a square v square. Then we write this expression as du d theta whole square. This is equal to a square v square minus mu by a to the power 4 v square into 1 minus a square u square. Otherwise, when you take square root of both sides, then this side is imaginary, right? And in similar manner, we get the integration as we write here directly a into du by root 1 minus a square u square. This is the left hand integration, and we take here also minus sign, and the right side is root a square v square minus mu by av into d theta. This is the right side, and integrating we get this side is here, this is cos inverse a, and the right side is similar, root a square v square minus mu by av into theta plus one another integrating constant, this is a2. Okay, so we get this is au into cos of, sorry, here we also apply the initial condition when theta this is equal to 0, u this is equal to 1 by a. So we get this is cos inverse 1 and this is 0 plus a2. If by a2 this is becomes 0, so by putting the value of a2 here, this is 0, we get au this is equal to cos of root a square v square minus mu by av into theta, and here we put u this is equal to 1 by r, so we get the result as r cos root a square v square minus mu by av into theta, and the right side is equal to a, and clearly this is the second result. This is the second result we have required this. Okay, so this is the first result of the first case, and this is the second result. Clear? And this is very interesting and important problem of central orbit. Thank you for watching.